So, good morning, good afternoon, good evening, everybody, wherever you are in the world. This is Tim Collins, Secretary General of the International Stainless Steel Forum, and it's a pleasure to welcome you all to our first autumn series webinar. This one is entitled The Marvels of Stainless Steel in Construction, and the banner screen is a fantastic image from New Plymouth in New Zealand, an amazing structure, and I think starts to showcase the sorts of things that we will talk a little bit about this morning. Not everything, unfortunately, is as sexy looking as this. This is quite a spectacular structure. But today, I'm going to talk through 6 things. So we'll start with a short introduction to set the scene. Then I'll talk a little bit about stainless steel's made simple. So a quick wander through some of the key and interesting features of stainless steels for those people who are not completely familiar. Then we'll drop into a section on the sustainable credentials of stainless steel. Then the fourth section is to look at construction options using stainless steels. And before we sum up with a few summary points and conclusions, we'll look at 10 reasons why stainless steels are arguably the right choice. So there are a few interesting and provocative statements in the webinar today to try and sort of get people enlightened, warmed up, however we should describe it. And please place any questions via the chat function on your screen, and we'll take the questions at the end. I'll talk for around 40-45 minutes, and then there's plenty of time for questions. So I trust that will be okay with everybody. So, okay, an introduction, a bit of a hard-hitting slide, looking at the difference between, on the right-hand side, what I would term brutalist construction. We've all seen buildings like this, and then things on the left that look wonderfully stunning, but hey, you know, are they truly usable and functional? But I'm trying to sort of set out the extremes of design and considerations. But let's sort of take a journey back in time to start with. Development of construction materials has been a very, very long journey, and depending on which literature you read, construction materials have been there in the times before BC, so to speak, maybe 400 to 4,000 years before. It depends where you go and sort of research. Early buildings were made from sort of common growth material, leaves, branches, even animal hides. But we are a global nation of people that are driven by the need to adapt, innovate, and adopt. We're very inventive. So as time progressed, we started to use available materials, stone, clay, timber, and over time, we were able to move into the age of bricks and concrete, and then the Industrial Revolution came along and brought us an impressive range of materials, particularly alloys, more particularly steel. And although stainless steel came a little later after the Industrial Revolution, this notion of a revolution of architecture was what started to change the world and give us what we know today. And you know, we accept there are many materials, whether it be concrete, stone, wood, glass, steel products, aluminium, etc. There's a huge list. These materials are all commonplace and they coexist, and we don't see them as revolutionary. But within that family of materials, there are some things like stainless steels that are perhaps not considered as routinely as ourselves in the industry would like, or maybe should be when you start to look at the credentials. But just thinking about construction, this process has evolved over centuries, and it's been driven, as I said, by both technological advancements and the desire of us as humans to explore, to extract, to use resources, to create tools and aids to advancement, indeed to harness available energy. And whilst the Industrial Revolution brought us energy primarily from fossil fuels. That in itself is evolving, and we're very familiar now with other forms of energy. And throughout all this process, as a race, we've been innovative. We've been driven by improving the standard of what I would call our comfort in life, and that's brought about modern construction materials and supporting materials. But there is always a note of caution that the history of what we've done over the last couple of centuries has not always been environmentally friendly in all aspects. We can't change that. That's evolution, but we can do things to positively influence our construction choices and materials for the future. And you could argue that over the last number of decades, as we've become more aware that we fight the fire of climate change and its effects whilst we're still feeding the flames. We're driving around in internal combustion engine vehicles, having goods delivered in similar vehicles. So we all enjoy the benefits and comforts, but we're creating the problem, and things should and need to change for the sake of us all as a society. So we have an opportunity to make a real shift, a paradigm shift in our materials selection thinking. And I would argue that we should really consider materials that combine the following attributes. Low or net zero carbon materials. We're all familiar with these terms now, and that includes both the manufacturing footprint and the maintenance footprint. We should also think about materials that do not have indirect, or what I would call indirect, pollution baggage. So if you have to preserve things, where do those preservative treatments and coatings actually end up? Do they end up in the soil, back in aquifers that ultimately end up being consumed by humans and animals? We should think about reducing the usage of co-materials rather than think of materials as individual elements in their own sort of box, so to speak. And I think modern architecture is already used to that concept. As I mentioned, long service life materials are really important, and the zero maintenance or very low maintenance needs, these should be coupled in our thinking. But we also need to choose materials because we can't immediately slow down the impact of climate change. Materials that are resilient against that impact, because trying to fix things when climate change has got worse will be a much more difficult challenge. So the choice of materials now becomes really important for our future lives, our future benefits, and I would argue our future survival. We need to think about recyclability. The circular economy is really important, and we have to think, and it's becoming more apparent, I see it every day, life cycle costing and even life cycle emissions for our decision making. Maintenance is not somebody else's problem. We have to look holistically. So having set the scene, I would now like to move forward and just try and talk about stainless steels in a fairly simplistic and memorable way. So firstly, hey, for most people we understand, for some people maybe not, but it's all about chromium to start with. And this chart here shows, with the y-axis on the left, corrosion rate in millimeters per year, and on the x-axis on the bottom, chromium content in steels. And you have a red line curve that shows how the corrosion rate develops as you add chromium. And basically, the more chromium you add, the lower the corrosion rate of steel products. So on the left, with very low chromium content, you have carbon steels. To the right of the almost vertical red line in the early part of the chart, before the dotted vertical line, you have the non-stainless, the alloy steel category. And then when you get to 10.5% chromium and more, you're into the family of stainless steels. And stainless is stainless, as many people know, because of the passive or corrosion resistant layer of chromium oxide on the surface, which we'll take a look at in a moment. So chromium is one of the really important elements in making stainless steel corrosion resistant. So here's a quick overview of the passive film, and let's compare that with barrier layers. So in the top of this diagram, we have the notion symbolized of how the passive film works. So the spheres, the orangey colored spheres, are oxygen molecules. The blue section on the top is the passive film. Beneath that is the substrate, stainless steel. If you damage that passive film, the presence of oxygen immediately repairs the passive film. So the passive film is a fantastic feature of stainless steels, self-repairing, it's highly adherent, and it's very thin, 2 to 3 nanometers thick. Compare that to having to apply barrier layers, and typically 3 layers are applied. And when they're initially applied, all looks good. So you have the top layer, a protective layer, and a primer layer, which is the interface between the above layers and the substrate material. It's a much thicker barrier system, but over time, these layers loosen, and that includes galvanized coatings. We see all sorts of barrier layers ranging from paints to chemical coatings, but over time they do fail to adhere and they require ongoing maintenance. So a simple reflection of the 2 main options for protection against corrosion. One is driven by the chemical analysis and one is driven by man-made protection layers. So let's look now at the stainless steel families, just to try and put things in context. So very early stainless steels that were produced almost 100 years ago are in the martensitic family group, and they have high strength, reasonable ductility, but only modest corrosion resistance. And these are the chromium carbon steels or the chromium carbon nickel steels, or include, some would argue, the precipitation hardening group. You then have the ferritic family of steels, which are straight chromium or chromium nickel steels, slightly better corrosion resistance, and they are resistant to what is known as stress corrosion cracking, which is particularly important. And then also we have the austenitic group, which many people are familiar with, the 18-8, the 18-10 stainless, and the more highly alloyed group, with good strength, very formable, good to excellent corrosion resistance, and no ductile to brittle transition. So this is a very useful family of stainless steels. These are typically the chromium nickel steels or the chromium manganese nickel steels, and even some higher alloy variants. Now, sitting between them is the new kid on the block, the duplex grades. The new kid on the block, they're what, 90 years old or something of that order. But these combine the best of both worlds, the best of the austenitics, the best of the ferritics. Really high strength, good to excellent corrosion resistance, pretty good ductility, and good fatigue strength. And these are typically the lean duplex with 21% chromium, a little over 1% nickel, or the 22% chromium, almost 5% nickel, molybdenum steels. I'm getting my terms mixed up, so please excuse me for that. So they're the families, but I would argue when we're thinking construction, we should be looking at the duplex grades and the austenitic grades first and foremost, depending on the application. Now, I think it's appropriate to compare attributes of stainless steels versus some other common materials that may be chosen. In this case, I've put the austenitic, ferritic, and duplex stainless steels alongside each other and then compared them with carbon steels and aluminium, a common aluminium alloy. And this is simply color-coded for ease of understanding. So red is bad, green is good, yellow is somewhere in the middle. I'm not going to read out all those attributes in the vertical list on the left, but you can see quite quickly the relative differences. And you would argue that duplex stainless steel using this sort of classification looks very impressive. Austenitic stainless steel is pretty good, although the yield strength is poorer. And the other materials are somewhere between those features. And not all these features, and of course this is just a selection of features, but not all these features are demanded for every application. But when it comes to logical thinking, and I think particularly modern thinking, where life cycle costing and life cycle emissions are important, and the service life without maintenance is equally important, then this is where stainless steels start to have the leading edge. And people will of course say, hey, but stainless steels are expensive compared to other materials. And yes, they are, but it's how you look at, how you define expensive that is important. So let's just move forward before we come back to costing or pricing issues and just look at a couple of features. So here is a comparison of standard carbon steel versus duplex stainless steel in terms of strength and impact resistance. And impact resistance is effectively shown as any energy absorption. So if the carbon steel is our standard and has a yield strength shown on the chart, something close to 400 megapascals or a little less, the duplex stainless steel offers a much higher yield strength. Of course, we're not quite comparing apples with apples because stainless steels yield in a different way to carbon steels. But the energy absorption characteristics of a duplex stainless steel are generally significantly higher than that of carbon steels. And these products are really no more difficult to work with compared to carbon steels. So the benefits that a duplex stainless steel brings when you're thinking about construction is not just the corrosion resistance, it allows for a significant reduction in what we would describe as co-materials. Now, if we move on and consider corrosion resistance, and for people that have seen my presentations before, this is a standard chart that I use on a regular basis. And this chart compares proof strength versus the pitting resistance equivalent number, which is a way of measuring corrosion useful for chloride containing or marine environments. And you can see on here in the top left-hand side of this chart, carbon steel with its relatively high yield strength, but low corrosion resistance using this assessment method, which I would argue is pretty valid in a lot of situations. You have the vertical red line on the chart, which is the broad seawater threshold. So to the left of that line, these products are not really suitable for seawater applications. To the right, materials are, and this is a guide. Don't think this is an absolute market in the ground, because of course seawater conditions change depending on where you are in the world, but this just gives you a simple guide. So aluminium sits just to the right of that line, close to 316, but lower in strength. And then moving into that top right hand section, you have the family of duplex stainless steels. So I think this chart shows quite easily, if you're looking for that combination of strength and corrosion resistance, where you need to be considering your material choices. And of course, I could have littered this chart with many more alloys, but of course, we're talking primarily about stainless steels, and we're looking to compare that with other regularly considered construction materials in the steel family. So now, having sort of given an overview of stainless steels in a very simplistic and relatively fast way, I would like to take a few minutes to look at the sustainable credentials of stainless steel, because this is not fully understood by everybody. So I'll start with a wordy slide. So stainless steels, by and large, not exclusively, are manufactured with a high recycled content, and the production byproducts can be used for other applications, whether that be in roadstone, making bricks for buildings, and fertilizers. And there's different uses all over the world. So the steel industry generally is very good at reusing its byproducts. Production consumables are routinely reused. An example there is refractory materials can be converted into slag formers used in the furnace and steel making vessels, and then on to roadstone. Protective paper during the coal rolling processing can be reused many times and then recycled back into new paper. So both byproducts and production consumables are well reused in the industry. And we know from our history that when correctly specified, stainless steel will last for more than 110 years. The industry is not any older at the minute, so we can't state more than that. But in that sort of usage, when correctly specified, as I said, you'll get this lifetime with minimal or zero maintenance, which in itself delivers very low life cycle emissions. The products are fully recyclable. You can recycle 100% of stainless steels, and by and large, they are recycling ready at the end of their life. And the attributes, particularly with things like duplex stainless steels, do allow, as I've said, for a significant reduction in co-materials. And I would equally argue that the life cycle costs, again, it comes down to correct specification, are the lowest of all primary man-made materials. So they provide an interesting option. There is that upfront cost, as I've said. We'll talk a bit about that in a moment. So now we'll start to look at relative life cycle costs. So because we are bound by antitrust laws in the association, we can't give you absolute costs, but we could do a comparative or relative life cycle cost difference. And this is looking at carbon steel versus duplex stainless steel. This comes from a bridge example from a few years ago. And what I've done here is demonstrate the magnitude of 4 aspects: the acquisition cost of materials, shown in the purple box, the installation cost for the structure, shown in the green box, any ongoing maintenance costs, and they're all outflows of cash. And then the red box is income from recycling at the end of life. And the comparison here is between a carbon steel on the left and a duplex stainless steel on the right. And the differences are quite stark. With the carbon steel, you have a low acquisition cost, but a very high maintenance cost. And with the duplex stainless steel, you have a very high acquisition cost, but an exceedingly low maintenance cost. So you're reversing 2 features dramatically. What is interesting in this chart, and keen-eyed people will notice, is the income at end of life is broadly the same. And that's primarily because in the lifetime of a carbon steel structure, you have to replace elements of it on a fairly regular basis. So you're getting an income throughout the life from being able to recycle pieces that have degraded, and you have to take them away and put new elements in. So that's why those numbers look about the same. And what you effectively get is something of the order of a 20% lower life cycle cost when you choose for appropriate uses, in this example, duplex stainless steel over carbon steel. So we're not talking about a few percent at the margins, we're talking about a significant benefit. So I hope that makes sense. But it's also important to consider the life cycle emissions. And here in this chart, we're looking at, again, in structures, 4 materials: austenitic stainless steel, duplex stainless steel, carbon steel, and aluminium. And what's really interesting is not that any of these materials are sort of dreadful or horrible, but what you have to do over the lifetime. And this is quite interesting. So stainless steels, in this, we've assumed that the service life is 110 years because we can't say any more. I believe it is in fact longer. So this is a worst case for stainless steels. And carbon steels require some surface maintenance every 10 years and some partial replacements about every 40 years. Aluminium requires some surface treatment about every 20 years, and arguably full replacement every 80 years. But what this shows is the growth of life cycle emissions, starting with the production emissions of the material on the left-hand side in year 0, and as the years progress, how the emissions build. And there is no doubt carbon steel, with all its attributes, starts in a much stronger position with a very low emissions profile, and stainless steels are higher, and aluminium even higher. And for aluminium, the data has been normalized to allow for its lower density. And this chart is not meant to be absolute. This is meant to be a useful guide. So we're not trying to get every feature, every point on the chart to absolute precision, but it's the trends that are important here. And what you see is when you're looking at structures, stainless steels really start to display their benefits after about 40 to 50 years in service, because the life cycle emissions broadly do not change, because they do not need that ongoing maintenance and repair and surface treatment or cleaning in the same way. So I believe this is very useful data that we should consider when we're thinking about different material choices. But are stainless steels actually a material selection dilemma? We've talked about the upfront costs, and many people really avoid stainless because they say, hey, just can't afford this stuff. I know it's great, but the material cost is so much higher. But is that the right way to think? You know, are we completely driven, are our mindsets firmly in the upfront costs, and we don't think about what comes next? As I said, maintenance is not somebody else's problem. So what are we trying to do when we build something new? Are we trying to build something that is both safe and secure, that looks good, has really innovative function and form? Are we really thinking about a low or zero maintenance concept? Do we equally think, I think people are thinking now, but I'm not sure we did in the past, about a low or zero materials carbon footprint, and that's across the life? Do we demand service lives of at least 100 years? Do we think about what's going to happen in the future as climate change does get worse? Will our choice of materials actually be resilient? Because as I've said, replacing things when climate change has got worse will be very, very challenging. So why would we not think in this way? Is it down to established norms? We've always done it this way, it works, it's good enough. Is it cultural rigidity? Can we just not think at the moment outside the box? Is it education? Is it lack of awareness? Or are we driven by what I would argue is short-termism or capitalism? We build, we commission, we sell for a profit. Hey, job done, we're all happy. But are we? Is that the right way to think? And I would argue that what we should really think about is the concept of fit and forget. So how often do we actually consider that notion up front? So let's move forward and just look at some of the material strengths in sort of summing up in this section. Stainless steels, I think we all know they're hygienic. They're inert, they don't react with other things. They're corrosion resistance, we know that. They have high strength, particularly the Duplex stainless steels. They are no more difficult to work with than carbon steels. They're easy to form, they're easy to weld. They are fire resistant, so they have some good characteristics there. They have excellent energy absorption characteristics, as I've said, particularly the Duplex stainless steels, but also the austenitics, which I didn't show on the chart earlier. When you specify these products correctly, they require very little maintenance, often zero maintenance. But note of caution, if you don't match the grade you choose to the environment, and there are many examples of that, stainless steels will corrode. So understanding the environment and understanding the credentials of stainless steel is really important when it comes down to material choice. These materials are resilient against the impact of climate change, and they have a low manufacturing CO2 footprint. It's not the lowest, but over the life cycle, it becomes very interesting and compelling. So now let's move on to looking at some construction options using stainless steel, and this will encompass some things that are about to hit us globally in the next few months. So I think we probably understand that designing with stainless steels has not been an easy ride. There's been a historic lack of design standards and associated design guides, which has meant that for people that want to choose stainless, and you'll have seen from the photographs, a lot of people have actually chosen stainless. There is a need for bespoke calculations, which is always less attractive for design engineers and architects, and that includes the determination of safety factors in construction. So historically things have not been easy, but some people have broken through that, which is great. But it would be good if more people were thinking in the way of choosing stainless up front. But let's look at a couple of key differences. So the Young's modulus and yield stress of stainless steels is very similar to that of carbon steel, but it's the form of the stress strain curve that is fundamentally different, and you can see the example of that in the bottom right hand corner of this screen. The dotted black and yellow line is the carbon steel line, and the curved orange line is stainless steel. So carbon steel has this sharply defined yield point with a plastic yielding plateau followed by strain hardening on the horizontal part of the chart, and stainless steels exhibit yielding behavior that is gradual with high strain hardening. So there is a difference, and we can use that to good effect. Now we also need to think about why, what would drive people to select stainless steels. Some of these things are obvious and well known, some are less well known. So corrosion resistance, everybody thinks about corrosion resistance for stainless steels, and everybody thinks about how they look. They definitely have a wonderful visual appeal. But the high strength feature, because the duplex stainless steels are not so well known, is often not appreciated or even overlooked. However, there are other features, and now we can start to exploit the strengths of stainless steel. In some installations, the ability to inspect those installations or indeed maintain them is difficult or virtually impossible, because you're trying to shoehorn structures into tight spaces or difficult environments. So in areas where you really don't want to think about regular inspection and maintenance, or you think the costs associated with those will be high, then choosing stainless steels becomes very interesting, because you can take away those features. The other interesting issue is when you're looking or working in low temperature environments and you want good toughness, again, it's an important driver for selecting stainless steels, because the austenitic stainless steels don't suffer the ductile to brittle transition, and whilst their strength is not as good as duplex stainless steels, even the duplex stainless steels will work well down to around -50 or -60 degrees centigrade. When you want a low manufacturing emissions footprint, which is becoming more and more important within the ISSF, more than 25% of our inquiries now are requesting this sort of information. That was less than 10% of inquiries only 2 years ago. So stainless steels fit well against that profile, and particularly over the lifetime, as I've demonstrated a few moments ago. Hygienic properties we know are important. Long service life, I mean, I argue we should be looking at more than 100 years of service life, but certainly more and more structures are requesting significantly more than 60 years. That still brings stainless into play. And stainless steel is a material that can be both reused in their structural forms and recycled easily at the end of life. So this fits very nicely with the circular economy profile. So in order to aid the use and choice of stainless steels in construction, there are some changes on the near horizon. And the first of those is the new American Institute specification, Aisc 21, which will be published formally in November of this year. And this covers structural stainless steel in buildings and will encompass the design, the fabrication and the erection of buildings containing both austenitic and duplex stainless steels. And this is an important change because, as I said previously, people had to do the calculations manually. And whilst this is an American standard, it is used in many places across the world, as I think people in the audience will know. There's also Aisc 313-21, the Code of Standard Practice for Structural Stainless Steel Buildings, and this sets out the criteria for trade practices involved in design, purchasing, fabrication, and erection of structural stainless steel buildings. So, as I said, this is November this year when these documents come out, and they will allow us to choose and design with stainless steels more easily. There's also the associated design guide, which will come out next month in October, Design Guide 27. And this is written for engineers who are used to working with carbon steels, particularly in structural components, but not necessarily with stainless steel structural components. So this is a very helpful guide for those engineers. And it applies to structural hot rolled components or welded open sections, and also rectangular and round hollow structural sections. So as I said, this will be out next month. We also have the Asce Standard 8-02, which again will come out November of this year. This is a major revision that supersedes quite an old version, the 1974 edition, and this applies to structural stainless steel components or members that are cold formed. So this is different to the other specifications and design guide I was talking about, and it covers cold roll sheet, strip, plate, flat bar, and this is for load carrying purposes in buildings or other statically loaded structures. So this is another complementary specification that is coming out. And what are we talking about in terms of components when we talk about these things? So here we have a selection of the hot rolled and cold form structures ranging from fasteners and fittings, I-beams, reinforcing bar, solid bar, hollow square bar. So you can see the range of components, but fundamentally we're talking about load bearing components. So these new specifications and standards and design guides cover these sorts of products in load bearing applications. But the one thing we shouldn't forget in all this, and we see many examples of this every day, is that on top of the structural components and the structural opportunities for stainless steel, there's also the aesthetics, the stainless facades, which have been used for many years and we're very familiar with, and I think most people would argue they're highly attractive. So those features are still there and are really the icing on the cake. You know, having built the strong and resilient and long-lasting structure using stainless steel structural components, the finishing touch is to make the whole thing look stunning and innovative and very beautiful. So we should never overlook the opportunities that facades bring to accentuate the modernism that stainless steel has as a material choice. But where do we go next? I've talked about the American standard, but there's also some work being done for the Eurocode standard too. So Eurocode 4, the rules for stainless steel composite beams, is something that is being attacked now and will be completed next year, 2022. And there are several phases to this, essentially 3. So the phase 1 is looking at the carbon steel rules that require modification for being able to use stainless steel in these sorts of applications. Phase 2 is about the numerical analysis to develop the new rules for stainless steel, which is probably going to drive some level of testing, physical testing, that will be required. And then Phase 3 of the preparation of guidance within a technical specification, or indeed the Steel Construction Institute publication. That is yet to be decided. But when these rules are developed, they can ultimately be converted into US rules as well. So there will be a natural fit, but not until 2027. So we're still 6 years away, because that's the sort of revision period for the American standard. So the work that is ongoing now doesn't just cover the American standard, it's looking at Euro codes too. So now I'd like to sort of summarize the construction options before sort of wrapping this up. So we shouldn't discount stainless steel as a material of choice, but we do need to lose our old school thinking. The new specifications and design guides will be game changers, so we can consider stainless steels more easily and with confidence. But we can't walk away from life cycle thinking. It becomes very important now, and particularly to offset the effects of climate change in terms of making our structures long lasting. We know that stainless steels complement other materials perfectly, and stainless steels align equally well to green urban space development. And a great example of that is one of the bridges in Japan that was recently replaced. It's a combination of timber and lean duplex stainless steel. So timber above the waterline, duplex stainless steel below the waterline. This is the Giboshin-Bashi Bridge in Japan, and it's a beautiful structure, but it's a lovely use of complementary materials in a specific application, maintaining the historical features and attributes with the longevity that stainless brings. So, getting into the last section, why are stainless steels the right choice? And there are 10 reasons I've put together here. 1, stainless steels are easily recyclable. They're recycling ready. They're a really powerful contributor to the circular economy. Number 2, these are pan-generational materials. They will last a huge amount of time, as depicted by the Chrysler building on the left-hand side of this diagram. It's been in situ for just over 90 years now. It's been cleaned 3 times with household detergent, nothing more. Very simple. It is the fit and forget solution. Reason 3, it's a wow material, without a doubt, whether it's in its natural state, or in this example, the Prairie Fire Museum, the enhanced state. Stainless steel always looks good. Number 4, it does have a futurist alignment, and that's whether you think about stainless steel rebar in the left-hand picture, so some of the beautiful structures shown in the other part of this slide. And it offers significant lightweighting potential in all applications and usage sectors. So that brings design opportunities that can be really exploited to look fantastic for many decades to come. There's no doubt that stainless steels have amazing physical attributes. Just a few are listed here, whether it be high strength, impact, absorption characteristics, the corrosion resistance, the not being susceptible to brittleness and elevated temperature resistance. This is a gem of a material, but as I said, you have to choose the right type of stainless steel for the right application. It can be easily reused. Many product forms can be salvaged and reused many times over. Reason 7, it is environmentally friendly. It has very low life cycle emissions in terms of its footprint, low life cycle costs, maintenance free, it's long lasting, it's non-polluting, it's essentially inert. You don't require surface treatments. This is a gem of a product that perhaps we don't fully appreciate. And you can see some of the uses there. It's construction, it's healthcare, domestic uses. There are so many uses of stainless steel, not all sexy, but all valuable. It's completely sustainable, and here you see the sort of cycle from scrap through steel making, finishing, production of components to production of structures. It's a perfectly sustainable material. It is decarbonising because you can install it and forget it. And there's a couple of examples here. The Chrysler building, which I've already shown, but the Samuel de Champlain Bridge in Canada, designed purposely with 15,000 tons of stainless steel for a service life of over 120 years, maintenance free. So this is a great example of beautiful structure that allows economies to flourish. And number 10, it's highly versatile, can be used in so many applications, from water supply to sanitation to transport, healthcare, land protection, etc. It's a highly versatile material. So I'd now like to wrap up, because I think I've about come to the end of my speaking time. What do we know? Climate change is exacerbating events that will cause structures to fail. And we've seen examples of that in recent years. Sustainability and resilience are a primary requirement, not just for construction, but for green urban development. We know that about 70% of our global society live in urban environments. There are many new opportunities now for stainless steels in construction, particularly with the new specifications and design guides coming out or on the near horizon. We need these standards. They're essential to make life easy for the engineers, but we also need to consider life cycle costing and life cycle greenhouse gas emissions. These are, I would argue, construction imperatives. And a question, do we always want to adopt the same old approaches, or do we want to be like our forefathers, completely innovative? We have to push the boundaries. Our society is founded on drive and invention. So stainless steels are, without a doubt, I would argue, a family of marvelous materials. We can select stainless steels with absolute confidence. The opportunity sits here. It's right here, it's right now. Stainless steels provide the opportunities for beautiful, futuristic designs, complementary material thinking, pan-generational structures, and protection of our land, our economies, and first and foremost, our people. If we only begin to think stainless when climate change has taken a hold, we will truly not save our planet. I'm not saying stainless is the only choice, but it should be one of those that is up there with the best other materials. So at that point, I'd like to thank everybody for their attention. I'd like to remind people of a great statement from Peter Drucker, that in times of turbulence, the greatest danger is not the turbulence, it is to act with yesterday's logic. Thank you very much. Do we have any questions, Joe?
Thank you, Tim. There was one question that already came in during the session. It is about slide number 12. Maybe you can go there.
Ooh, let's drift back.
Yes. And it says, can you please explain a little bit more in detail why Fritics have yellow color in life cycle emissions?
Yes, so this is not to say that Fritics are necessarily bad. And of course, we have to consider in the context of this presentation that we are looking at construction materials. But a great example I came across quite recently was the use of some ferritic material in it was in fact last year, in a sea defence wall. And whilst the material was still perfectly intact, it was corroding, and there was some maintenance guys actually clearing off the corrosion from the exposed surface, so effectively grinding it off and using pickling paste to repassivate it. And I stopped and chatted to these guys and said, hey, you know, have you done this before? And they said, yes, we have in other areas. We don't have to do it too often, but every few years we have to come and do this work. And of course they have to drive out to places which creates emissions. They have to buy all the products for the work. So that was one example where it's not that Fritics stainless is a bad materials necessarily, but in these sorts of applications, and particularly when you're in a marine environment, they're not necessarily the right choice, because this ongoing requirement for maintenance and making things look good adds to the emissions. And we shouldn't forget that mobility accounts for 25% of our global greenhouse gas emissions. So there's a lot of downsides of having to maintain and repair things from an emissions perspective. It's not just about the material. So I hope that answers the question with a nice example.
Thank you. There's another question. Is there any talk of developing a stainless steel blue book?
Okay, good question, and the simple answer is I don't know, but I do know somebody who will know the answer to that. And if we've got the email address of the person that's asked the question, I will find out and send an email in response.
Okay,
so I can't answer that question directly, but I can find out.
Okay, we will certainly send a message. Then there's another question about duplex stainless steels, and it says, if duplex steels have been around for 90 years, what has stopped us from using them more widely in construction? Has it been driven by costs or a lack of knowledge of the material behavior?
I think it's both of those things for sure. Duplex stainless steels today still only make up a little less than 2% or around 2% of total stainless sales. And of course, when we're looking at construction, stainless has not been a huge material usage category in construction, although there are some wonderful examples now that have come about in many in recent years, but some going back to things like the Chrysler building are still quite old. So one thing is duplex steels people are not so aware of, without a doubt, and there is a need to educate relentlessly on the great credentials of the duplex family of stainless steels. I think the other thing to say in duplex stainless steel, we do now truly have a family of duplex stainless steels that allows flexibility of choice, and that didn't exist too many years ago. Most duplex stainless steel was focused on the 2205 duplex, and now we have a much broader family. So I think the opportunities for duplex, particularly in construction, are with us in more recent times. But I think there's a cost fear and there's a usage fear. People still have a fear that stainless steels generally, when you're thinking about working with them, are difficult. And it's not difficult, it's different. They are no more difficult. You just have to understand the different care and attention that stainless demands over carbon steels and other materials that have been used with confidence for many, many decades. And there is also, you've also got to overcome the fear factor that when you change, you have to change thinking, you have to change the way you work. It's not, as I said, difficult, it's just different. So I think we have a relentless task ahead of us to educate the world in the attributes of duplex stainless steels, because I would argue they are a wonderful part of the stainless family. They're a family in their own right. But if we don't talk about them, we don't let people know, and people only think there are two grades of stainless steel. Still to this day, I get comments where people say, well, there's only 304 and 316, isn't there? And of course, it's not right. So as an industry, we have to promote duplex stainless steels if we want to be taken seriously in the construction world. I hope that answers the question.
Thank you, Tim. There's a question here, people asking if they can get a copy of the slides. Yes, both the presentation and the video will be available after the second session this evening, or at the very latest tomorrow. And then there is somebody seeking your opinion on how you feel, what do you think about the QN series stainless steel, which are produced by Qingshan when they are used in construction. What do you think about that?
Well, the QN series, I must admit, I'm aware of, but I'm not knowledgeable about the details. So maybe that's something I just need to do a little bit of research on and then offer opinions. Because I think one of the things about our industry is, in all parts of the world, we have been very innovative in developing different stainless steel products and variants of our products. And there are certain things I'm aware of without knowing the detail. I would not argue that anything is necessarily bad in the stainless family. It's all about the right choice for the right application. So that's certainly something I can take a look at and then drop an email with my sort of views and opinions. But I mean, again, it's a question of choosing the right material for the right application. And when we're talking construction, you know, I would be focused more towards duplex and austenitic type stainless steels, or stainless steels with those attributes, than other stainless steels from the total family.
Yeah. Okay, first question. Are duplex steels more difficult to produce?
Whether they're more difficult is an interesting question. I would argue, because I've worked with the production of duplex steels for many years, they're actually not. There are some things that take a little longer because of the physical time it takes to undertake certain processes. But in terms of difficulty, no, once you're used to them, they're quite straightforward to process, I would argue. They just demand a little more understanding of the production conditions.
Okay, thank you. The next question is related to slide number 17. So maybe we can go to that slide. So it's
I'll go back. If I can remember what slide 17 is. It was that one, wasn't
that was
it?
slide 17. On this chart, why is the installation cost for duplex lower than that for carbon steel?
Because you only do it once, and I know I didn't mention that, but with stainless, with carbon steels, you'll have to reinstall some things. So you've got a maintenance dimension. I should have mentioned, and apologies for that. You've got an additional installation dimension too, so that's why it pushes it slightly higher.
Okay, thank you. Next question. Are there any developments in material finishes, like matte finishes for duplex materials, polishing techniques or something?
It's a good question, and that's probably one better directed at people who undertake these finishing processes. But there are no real reasons why duplex shouldn't attract the same sort of wonderful finishes that other austenitic stainless steels do, really. So those opportunities should be there in exactly the same way. But if the person who's asked the question would like more detail on that, I can certainly get that and forward a response by email.
Okay. Then the following question: in the architecture, engineering and construction industry, which material is more versatile and aesthetic, aluminium or stainless steel?
But aluminium is a fantastic material, without a doubt. But it does have limitations in terms of its strength. I think that's a well-established feature. You can alloy aluminium to improve its strength, but then that comes as a downside cost. Of course, it has the benefit of being a very light material, so it has some great benefits there. But whilst it does have a passive layer, the layer doesn't survive as long as the stainless steel layer. I think that's well proven already, and it can be damaged much more easily. So I think there are many applications where aluminium is exactly the right choice, and even in construction, and I would love to see more aluminium used. But I think the opportunity that particularly duplex stainless steel presents is the one material game changer for construction, because people are less familiar with the credentials of duplex stainless steel. So where you want strong structures that will last for a very long time and reduce the overall material content, I think duplex surpasses aluminium for sure. We also have to recognise that the emissions footprint for aluminium is sadly not as good as that for steel products, because it is so highly energy intensive, even with a reasonable amount of recycling. So you'll see even on aluminium cans, for example, the declared recycled content is not much above 40%. So it is a problem for the aluminium industry. It's something that's recognised, but the energy consumption footprint is not going to go down, because there are so many regular daily household uses for aluminium. So I think aluminium has some challenges, even though it's a great material. So I hope that answers the question in a fair way.
Yes, there's one follow-up question on that particular one. Which one is more corrosion resistant?
The answer to that is it depends on the environment, because corrosion in itself has many forms, many types of corrosion. So you have to first understand the environment that the material needs to operate in, and then you choose the right material for the environment. So you cannot just say which is the more corrosion resistant, because you have to understand whether you've got pitting corrosion, stress corrosion, galvanic corrosion, or a multitude of these mechanisms before choosing the material. So it's not a simple question. And I don't know if the sort of person in the audience saw the Understanding Corrosion webinar from last year that we did, but that's available on YouTube to sort of go and look up and gain more insights. And I'd sort of say, please take a look at that, and you'll perhaps understand why corrosion is not such a simple topic to answer the question in an easy way like that.
Okay, thank you. We can send on the link to that particular webinar also, if needed.
Yeah, great idea. That'd be good.
And then we're staying on the slide you've put on, this slide number 17. Could you clarify the concept of income?
Yes, very simply. So when something reaches its end of life, whether that be when it's going to be decommissioned and changed completely, or you have to take some partial component of the structure away and replace it with something else, you can sell the recyclable materials and get an income stream from that. And that is quite worthwhile. Of course, scrap metal prices do vary quite wildly at times, but it is a valuable income stream and should not be forgotten about when undertaking life cycle costing. And certainly there are companies out there who will do dismantling and decommissioning of facilities for no charge, because the income stream they get from recycling materials is so large.
Okay.
Hope that answers the question. Yeah.
Yes, and otherwise we can always, you know, come back afterwards to clarify it even more. Next question, what is the role of Fritics and its share of overall stainless steel production?
Yeah, I mean, Fritics have a very important role in the overall stainless world, and Fritics are used in a variety of applications, whether it be in sort of household goods, domestic appliances. But when it comes to construction, I would argue that Fritics could be used for decorative aspects of construction, but maybe shouldn't be used for structural load-bearing components. So I think the opportunities that are presented by both austenitic and particularly duplex stainless steels when you come to load-bearing components are much more important than those for ferritics. So ferritics are an important part of the family, and a question I got from the session earlier today was, you know, are there any examples of where ferritics really sort of don't work? And I touched on an example I saw last year where ferritics had been used in a structure for coastal protection, and the material was rusting, and there were some engineers actually grinding away the corroded sections and repassivating with a pickling paste these sections. And that comes at cost. It comes at additional emissions, or comes with additional emissions, and becomes an ongoing task. So I think you have to think about your choice of materials in the environment very carefully. So ferritics have a place. They're a great material. They're of course generally nickel free, which lots of people like, but be very cautious when you're thinking about structural structural applications. Any other questions?
No, it seems to be the last question, unless you want to. Oh no. Next question. What does the lack of nickel do?
What does the lack of nickel, was that?
Yes, the lack of nickel. So probably, you know, in ferritics it says.
Yeah, well, I mean, basically you're changing the atomic structure. When you add nickel to stainless steels, you change the structure from a body-centered cubic structure to a face-centered cubic structure, and that improves the formability quite dramatically. So the highly formable stainless steels do tend to contain nickel, but in recent times, formable low nickel or nickel-free grades have been developed, and of course there are grades where manganese is substituted instead of nickel to get similar results. However, manganese is quite a volatile commodity from a pricing perspective too, and I guess most people know that nickel is equally. So it's always a difficult line to tread if you want to choose low nickel or nickel-free steels, and I think that's why the duplex family become important, because they are low nickel first and foremost, and so you do tend to get some price stability caused by the low levels of nickel in duplex stainless steel. So I hope that sort of answers the question from a number of perspectives.
No more questions now.
Okay, well, I hope people found the session today informative, provocative in parts, and stimulating. And as I said, everybody will get the presentation. And if anybody has additional questions that they think of after the event, my email address is contained within the presentation. So please email me and we'll answer quickly. So I'd like to say to everybody, take care. Thank you for joining. Stay safe. And hopefully we see you at one of our webinars in the near future. Thank you very much. Bye-bye.